Okay, hurricanes. I'm sure everybody knows what a hurricane is. It's one of these guys down here. I believe this example down here was from the 2005 hurricane season. A lot of you guys are probably a little young to remember this in detail, but 2005 was the most active hurricane season we've had in the last several decades. And we had Hurricane Katrina and Hurricane Rita, both of which came on shore on the Gulf Coast and caused significant damage, as well as Hurricane Wilma, which was one of the strongest hurricanes on record in terms of its central pressure. All told, in the 2005 hurricane season, the hurricanes were responsible for nearly 4,000 fatalities, as well as $160 billion worth of damage. So it's a pretty big deal. Hurricanes can be a big deal in terms of fatalities and damage. Okay, so let's give a working definition of a hurricane. What is a hurricane? Well, for our purposes, we could say that a hurricane is an organized tropical storm system. An organized tropical storm system featuring vigorous convection. Now, I should point out, when we talk about convection in the context of hurricanes, we're talking about thunderstorms, basically. So you can interpret, when we say convection, you can interpret that as thunderstorms. You'll recall that from the beginning of the course that this term convection refers to heat transfer, in particular heat transfer upward. But in this context, the things that are transferring the heat upward are the thunderstorms. As the warm air in the thunderstorm rises, that transfers heat upwards. So thunderstorms are examples of convection. Okay, so it's an organized tropical storm system featuring vigorous thunderstorms and sustained winds in excess of the threshold for sustained winds that we need to be defined as a hurricane is 64 knots. Winds in excess of 64 knots. Or if you don't like knots, you want to convert that to miles per hour, that's 74 miles per hour. So that's our cutoff. That's our defining point for a hurricane. It has to be winds of at least 64 knots or 74 miles per hour. So let's unpack this definition here a little bit. So what do we got? So first of all, it's an organized tropical storm system. Let's focus on this tropical part first. So hurricanes are tropical systems. You don't find them in mid-latitudes. You don't find them at the poles, obviously. You only find them in the tropics. We'll talk about why that is later, but the basic reason is that you need a whole lot of water vapor to drive all these clouds, which means that these systems have to form over warm water so that you can continuously pump water vapor into them. And so it's an organized system featuring vigorous convection, and that's basically what a thunderstorm is. That's basically what a hurricane is that it's a bunch of thunderstorms organized around a central eye and rotating around the eye. So at its heart then, a hurricane is really just a collection of thunderstorms, which means that hurricanes inherit a lot of the same kinds of things, same kinds of characteristics that we talked about when we talked about thunderstorms. In particular, the energy source for this system is going to be condensation and latent heating in the clouds, just like in thunderstorms. And you need a conditionally unstable environment to allow the cumulus clouds to form. So those things are just like thunderstorms. The one thing that's a little bit different is that when we talked about thunderstorms, we pointed out that for an individual thunderstorm, the more shear you have in the environment, that is, the bigger change in the winds with height, the more likely it is for the system, for that thunderstorm to be a severe storm. So for individual thunderstorms, wind shear results in severe storms. For hurricanes, it's exactly the opposite. For a hurricane, they tend to not like wind shear. They tend to not like changes in wind speed with height. We'll see why that is later on. But if you have very strong shear in the environment, it actually tends to inhibit the storm from forming, from organizing. Now, it's worth noting that these storm systems have different names in different parts of the world. So where we are, here in the Atlantic and in the Eastern Pacific, they're called hurricanes. So we're in our part of the world, in the Atlantic and the Eastern Pacific, they're called hurricanes. On the other hand, if you're over here in the Western Pacific, here over near Asia, these same storm systems over here are called typhoons. They're the same thing, they just have a different name. So if you've got one of these systems that's impacting Taiwan or Japan, then in that case, that's going to be a typhoon. Whereas if you're in the southern hemisphere, so if you're down here by Australia, for instance, in that case, they just refer to them more generically as cyclones. So they don't use either the hurricane or typhoon, they just say cyclones. That's also true in the Indian Ocean here. So if you're in the southern hemisphere or in the Indian Ocean, they're typically referred to as cyclones. Now, I wouldn't get too hung up on the names here. It's the same system, same physics, just given by different names in different parts of the world. Right? It's like in the US, we call them potato chips, and in the UK, they're potato crisps. But they're the same greasy slices of potato, fried potatoes. Or in the US, it's ketchup, and in Australia, they call it tomato sauce, which I guess makes me wonder what they're putting on their spaghetti. But in any case, it's the same system, regardless of what you call it. Now, in order to become a hurricane, one of these systems typically goes through a series of stages. And as you'd probably expect, we give these stages names so that we can refer to them. So sort of the earliest stage in the formation of a hurricane, it's what's referred to as a tropical disturbance. Tropical disturbance. And tropical disturbance is kind of a loosely defined name. It's just a term that's given to a large collection of thunderstorms in the tropics. It's probably a decent way to phrase that. It's kind of a system that kind of has the look that it might be something that could develop into a hurricane. It's referred to as a tropical disturbance. Now, as the system grows a little bit and starts to become organized, the next stage in its development is called a tropical depression. Tropical depression. And this guy, tropical depression, does have a more specific definition for it. In this case, it's called a tropical depression once the winds in the system start to exceed 20 knots. Which I guess would be about 23, 24 miles per hour. If it continues to develop and get stronger, the next step in its development is referred to as a tropical storm. A tropical storm. At the tropical storm stage, that's when the winds in the system are in excess of 34 knots, which I guess is close to 40 miles per hour. These are sustained winds, remember? And at that point, once it gets to the tropical storm stage, it officially gets a name. So tropical storms are named systems. And then, of course, if it continues to develop, as we said before, so that the winds reach 64 knots or 74 miles per hour, it becomes a full-fledged hurricane. So this figure down here shows a snapshot which has systems in different stages of development. These are not the same storm. They're just happen to be storms that are happening at the same time in different stages of development. So we've got some labeled over here. So for instance, this system down here over, I guess this is sort of the Panama region. It's just a big old collection of thunderstorms. And so this is what you might refer to as a tropical disturbance. It's not very well organized yet, but it is a pretty large collection of thunderstorms, which has maybe the look that it could organize into something stronger. And then over here, I guess off the coast of Costa Rica, here in the Pacific, we've got something which is also a big collection of thunderstorms, but it's a little better organized here in this system. And the winds associated with this system are a bit stronger. This guy is a tropical depression. So that's our second stage. Over here, we've got a full-fledged hurricane. And then up here, we've got a system that's a tropical storm here. And it's worth noting that these stages go in reverse also. That is, if you're a hurricane and then you begin to weaken, you start to go through the stages in reverse, first becoming a tropical storm and then a tropical depression and so forth and so on. And I'm guessing that this system up here, this one sort of off of Baja California, this guy up here is probably a system that is decaying. That is, it might have been a stronger system, perhaps a hurricane at some point, and so it's starting to die off, and at this point it's a tropical storm. It's been downgraded to a lesser category. So that at least gives you some idea of what these different stages might look like if you're looking at them on satellite images. Okay, let's talk a little bit about the structure of one of these systems. So now basically, again, a hurricane is just a collection of thunderstorms that are organized around a central eye. So this guy here is a radar image of Hurricane Katrina. And so it's showing half the storm here, and then it's got a cross-section, a cut through the storm, showing a radar image, where the redder colors here show stronger thunderstorms, if you like. More precisely, it's stronger rainfall here with the redder colors. And then we've got sort of the surface image of the radar pattern down here on the other side of the storm. And one thing you'll note is that the center of the storm is calm, right? It's completely clear in here. There's no rain in the center of the storm. And that's the eye of the hurricane. I'm sure you guys are all familiar with that. It's basically calm there because the circulation's set up in such a way as to get downward motion in the center of your hurricane. And that downward motion suppresses cloud formation. Now, as you go outward from the eye, you find that the strongest thunderstorms, the strongest convection, and the most dangerous part of the system is just outside the eye. This region just outside the eye has the strongest storms. It's the most dangerous part. And that guy has a name. So the band of strong convection, or strong thunderstorm, just outside the eye of the storm, that band of strong thunderstorms is called the eye wall of the hurricane, the eye wall. And you can see it here in this radar image. You've got this place just outside the eye where you've got the deepest red colors right in here on both sides. And that's telling you that's where the strongest convection is. That's where the strongest storms are. And that's the system's eye wall, just outside the eye. Now, if you continue going outward from the center of the storm, what you find is that the thunderstorms, the convection is not uniform throughout the hurricane. Instead, you find that it's organized into these bands. You can see it here in the cross-section in the radar, where you've got your eye wall here with the strongest convection, and then we go outwards, and we've got these bands of strong convection here with stuff in between that's not quite as strong. It's still stormy in between, but it's not quite as strong as it is in these bands. And you can also see this in the satellite images, just of looking at the clouds, where you can see that the clouds organize themselves into these bands that are swirling into the center. So these bands that swirl into the center, so as the storms in the hurricane swirl into the center of the hurricane, they organize into what are called spiral rain bands. So these bands are called spiral rain bands. So as the storms are swirling into the center, they organize into these bands, these spiral rain bands. It's kind of an interesting thing. These spiral rain bands actually have some characteristics in common with squall lines. They're kind of bent. They're not straight lines like squall lines. They're kind of like taking a squall line and wrapping it around the hurricane. But in other ways, they have similar characteristics. They have their own cold poles, which sort of propagate out away from them and cause lifting of the air out in front of them, and so forth and so on. So you can think of those spiral rain bands as sort of being squall lines that are wrapped around the center of the hurricane in some ways. What about the winds? So over here we've got an image showing the wind speeds. This is the wind speeds down near the ocean surface in a hurricane. I guess this is Hurricane Dora in this particular example. And so the bluer colors are weaker wind speeds and the redder colors are stronger wind speeds. And you can get a sense of the circulation from the arrows as well. The first thing to note is that the winds are counterclockwise around the low center. So that's what we expect, right? It's just like mid-latitude cyclones. If you have a low center, the circulation around that low center will be counterclockwise in the northern hemisphere, and it'll be clockwise in the southern hemisphere. In terms of the wind speeds, you see that the fastest wind speeds are kind of just outside the eye. The eye is fairly calm, again, because we've got the descending air in the eye. And fastest wind speeds are kind of just outside the eye wall. So it's not really right in the eye wall. In terms of the fastest winds, it's just a little bit outside the eye walls where you get this band of relatively strong winds here. You can see numerically on the color bar down here, so how the winds match up quantitatively in knots. And remember that hurricane definition is that you have to have at least 64 knots sustained winds. So the part of the system that has 64 knots is going to be this kind of orangish, reddish color, kind of right in here. And so you can see it's really just the center part of the system that has winds in excess of 64 knots. The hurricane speed winds are really just down here in the center part of the system, just outside the eye wall. Okay, now let's talk a little bit about how these things form. How do we get these hurricanes going? And you should keep in mind as we go through this that, again, hurricanes in a lot of ways are just big old heat engines. I mean, they're being driven by latent heating in the clouds. And there's a ton of clouds formed in the hurricane. So you got a whole lot of heating going on in the center of that storm. And that's what's driving this storm system. And so that means that the fuel for your hurricane is going to be warm, moist air that's feeding into the storm. We've got to have a source of a lot of water vapor to feed into that storm in order to produce all of that condensation and latent heating. Okay, so how do we get one of these things started? So with the next several slides, we're going to step through the development of one of these systems in terms of what's going on in the hurricane. And all of these slides are going to have the same basic format. We've got our ocean surface down here. Note that I've labeled it as warm because we're going to need a lot of evaporation, a lot of water vapor feeding into these clouds. So in order to sustain all of that evaporation, we need warm ocean water down here below. So we'll see later the winds actually contribute to evaporation as well, but that happens later in the system. And then above that, I'm showing various pressure levels here. So I've got the 990 millibar pressure level, 650, 400, pressure decreasing upwards, and then 200 here in the upper troposphere. So you can think of these guys as being analogous to the 500 millibar surfaces that we've been looking at. Just different pressure levels. So you can think of each of these as being a pressure surface here, just with a certain value of pressure. So typically we start off with not much going on, just warm ocean surface below. And then something happens in order to kick this off. Typically, as with cyclones, mid-latitude cyclones that we looked at earlier, we need some sort of pre-existing disturbance to come in and get things started. In the present case, it's going to be some pre-existing disturbance that propagates through and produces a little bit of low pressure down here near the surface. Now, there's a lot of different kinds of things that can do this, but one of the most common are these disturbances called easterly waves. There are waves that form over the highlands of Africa, and then they propagate eastward across the Atlantic. That's why they're called easterly waves. And often these waves, as they propagate across, they bring, a little bit of low pressure. In fact, they're waves, so they have low pressure and high pressure and low pressure associated with them. And as they propagate across, the low pressure associated with the waves can be enough to start to initiate one of these systems. So our starting point then is some pre-existing disturbance that propagates through, bringing with it some low pressure. And that low pressure, when it propagates over the warm water, will tend to organize some convergence, right? It's low pressure, so it's going to tend to draw some convergence into the low center. And if you've got convergence into the low center, then that's like squeezing the toothpaste, and so the air that's there is going to be forced upwards. So we're going to tend to force some rising motion then over the low center. And if you've got rising motion, motion in an environment with lots of water vapor, you're going to tend to produce clouds. So we're going to start to generate some clouds in the center of the system here. So you can think of this pre-existing low center then as sort of organizing the convection, the cloud formation, over a central low pressure system here. Now the other thing to keep in mind is that once you've produced these clouds, and I should note that when you draw this in your notes, it's probably a good idea to extend the cloud all the way upwards to the top of the troposphere here, like I did here, because what's going on at upper levels is going to turn out to be important later on. But in any case, as we draw the air into the low pressure system and it rises and produces clouds, remember that clouds are condensation and water droplets, and that produces latent heating. So you're going to end up getting a lot of warm air here sitting in the center of your system. So for that reason, hurricanes are referred to as warm core systems, because they have got warm air in their center, and that warm air is associated with the condensation in the clouds. Okay, so now the next step in the process, it has to do with the fact that you've produced warm air in here. And if you remember, when we talked about the amount of mass in between two pressure levels, we pointed out that between any two pressure levels, say 200 and 400 here, the amount of mass is always fixed, but the space it occupies changes. In particular, as it warms up, this layer will expand, and the same with the layers below it. So as this system starts to warm up at its core, the thickness of these layers between the pressure levels will start to increase. And so it might look something like this. Maybe I'll step back so you can see that again. So pay attention to the pressure surfaces here, which initially are flat, but as I warm up that air in the core, the layer in between, the layer here in the center is going to expand where it's warm. Bang, like that. Now, as these layers expand, the end result is going to be that up here at the top of the system, we're going to get the pressure surfaces bulging upwards, right? Because the layers below are expanding, and as they expand, you're going to end up getting the top of the sky bulging upwards. You can think of this as being kind of like a ridge sitting over warm air, although it's a very localized ridge just sitting directly over the storm. But any place where you've got your pressure surfaces bulging upwards, remember, that acts kind of like high pressure. In fact, it is high pressure relative to the air around it, because if you start out over here at 200 millibars and then go into the center, you end up below the 200 millibar surface, which means your pressure is bigger than 200 millibars. But regardless, we've got higher heights on our pressure surface here in the center, which means it acts like higher pressure, which means we end up producing a pressure gradient force pointing outwards from the center of the system. So kind of like this. So those two guys represent the pressure gradient force pushing outwards from the center of the system at upper levels. So notice at this point, what's going on at the ground is kind of the mirror image, the opposite of what's going on at upper levels. At the ground, we've got this low pressure here associated with the surfaces dipping downwards. Dipping downwards acts like low pressure. Whereas at upper levels, we've got the surfaces bulging upwards, and that acts like high pressure. And that high pressure then produces a pressure gradient force pointing outwards. So if we've got a pressure gradient force pushing outwards, you can expect that's going to drive some winds. And so the next thing to recognize in the development is that you're going to produce winds at the top of the storm system that are diverging away from the center of the storm, being pushed outwards by that pressure gradient. So that's sort of the next stage of the development. We get this divergence at upper levels in our system. But this is kind of like mid-latitude cyclones. If you recall, in mid-latitude cyclones, places where we had divergence, we're taking mass away from the air column. And when you take mass away from the air column, that reduces the pressure down at the ground. So when we start to drive some divergence here at upper levels, that's actually going to reduce the pressure down here at the surface. So the next step in our schematic here is going to be the pressure at the ground dropping. Now, if you look carefully what I did, so pay attention to what's going on down here at the ground, and in particular pay attention to this pressure surface. What happened to the pressure surface is it dips down even further. And so that represents the pressure getting lower because over here, you're below the 990 millibar pressure surface, which means pressure is bigger than 990. But then you cross it, and over here you're at lower pressure. So we've produced even lower pressure down at the ground. And I'm going to represent that by drawing in a big old L here at the bottom to indicate that we're reducing the pressure down here at the surface. And then once you've started to feed back onto the surface pressure, now you've started to produce a feedback loop, because as the pressure drops down here at the ground, you're going to draw more convergence. You're going to produce stronger winds around the low center. That's going to draw more water vapor into the clouds, which is going to give you even more convection, more latent heating. The system gets even warmer, produces a bigger pressure gradient here at upper levels, and drives even more divergence. Driving more divergence causes the pressure down at the ground to drop even more, which draws more air and water vapor into the system, which produces even more clouds and latent heating in the center, which drives a bigger pressure gradient at the top, which produces more divergence. And so you get a feedback loop, much like we had with the mid-latitude cyclones. It's a different feedback loop, but it's a loop that feeds back on itself and causes the system to amplify on its own. Okay, let's step through those stages here one more time, just quickly. So we start off with not too much going on. We've just got a warm ocean surface. In propagates a pre-existing disturbance, perhaps an easterly wave, causing a little bit of low pressure down here near the surface where the pressure surfaces dip downwards. That in turn is going to draw some air into the low pressure center, which is going to produce upward motion, which in turn is going to produce clouds. So it's organized convection over the low center. And those clouds, through latent heating, are going to warm the air here in the center of the system. As the air is warmed here in the center of the system, the layers expand. And that expanding of the layers ends up producing a place where you've got higher pressure surface heights here at upper levels, which acts like high pressure. And that in turn is going to drive pressure gradient force. pointing outwards on either side. That pressure gradient force here at upper levels is now going to drive diverging winds here at upper levels. And those diverging winds at upper levels are going to reduce mass from the column, take mass from the column, which is going to end up reducing the pressure at the surface. And reducing the pressure at the surface makes the system stronger, draws more air in, produces stronger winds, which in turn produces stronger convection and more latent heating, which results in a bigger pressure anomaly aloft, which produces more divergence, et cetera, et cetera. And so you get a loop that feeds back on itself and it amplifies. Here's what the structure might look like in 3 dimensions. So you can see you've got this is just schematic, it's not a real system, but you can see you've got your eye here where they've sketched in downward motion in the center of the eye. And then outside the eye, we've got our eye wall, and then our spiral rain bands as we go further out. And down here at the ground, you can see that the air is swirling in counterclockwise into the center. Now, one thing that's interesting about this is when you go to upper levels, you find the system actually rotates the other way. Because remember, at upper levels, the air is diverging away from the center instead of converging into the ground, or converging into the center, into the low. So at the ground, the air is converging into the low center, which produces counterclockwise rotation. But at upper levels, it's diverging away from the high at upper levels, which produces clockwise rotation in the northern hemisphere. So the system rotates in the opposite sense at the ground as it does at upper levels. This can often be a little bit confusing. If you look at a hurricane image that has a lot of cloud cover up at the upper part of it, then you might actually see the system rotating clockwise, which will be kind of confusing because hurricanes should rotate counterclockwise. But what's going on is you're just seeing the clouds up at the top of the system that are diverging away from the high, and so that air is rotating clockwise, but the air below it, down near the ground, being pulled into the low center, is rotating counterclockwise. Okay, so now that we know more or less how these systems form, let's go through and list the ingredients that we would need to produce one of these systems. And there's kind of 2 different categories. One category is thermodynamic, and by that I refer to things that generate changes in temperature. And down here at the bottom is mechanical. Those are the things that have to do with the winds. So in terms of the thermodynamic ingredients, what do we need? Well, the first thing we need is lots of water vapor to feed into all of these clouds. So hurricanes have a ton of clouds and a ton of latent heating, and in order to support all that, we're going to need a whole lot of water vapor. So lots of water vapor to feed the clouds, which in turn means that we're going to require warm ocean surfaces, warm ocean temperatures, if you like. Because in order to produce all of that water vapor, we're going to need a lot of evaporation. And in order to have that much evaporation, the ocean surface is going to have to be warm. If it's not warm enough, you won't get enough evaporation and you can't produce the system. So, first ingredient is warm ocean water, which is why these systems form in the tropics. The second ingredient we're going to need is a conditionally unstable environment. A conditionally unstable environment. To allow the thunderstorms to form. So again, you'll recall that thunderstorms are basically cumulus clouds, and cumulus clouds are clouds that form in conditionally unstable environments. Now, it turns out that in the tropics, the environment is almost always conditionally unstable. So the second ingredient here is almost always satisfied in the tropics. Okay, going down to the mechanical ingredients that affect the wind speeds. The first mechanical ingredient is that we're going to need an environment with relatively weak winds, or at the very least, weak wind shear. Relatively weak wind shear in the environment. So the system stays vertically aligned. So again, this is the opposite of thunderstorms. In thunderstorms, the more wind shear you have, the more severe the system. But in a hurricane, typically you don't want a lot of wind shear because you need the system to stay vertically aligned. So what do I mean by that? Let's step back and look at our diagram here. So what's driving all of this, the amplification of this system, is that the divergence here at upper levels, which takes mass away from the air column, has to be aligned over top of your low center at the ground so as to amplify that low center. That's sort of the thing that produces this feedback loop and allows the system to amplify. The problem is if you have a lot of wind shear, so if you've got winds up at the top of the system that are very strong, say, and winds down at the ground that are pretty weak, what it does is it's going to take the system and tilt it over a little bit. And so instead of having the divergence here sitting directly above your low center at the ground, you're going to take the divergence and move it off to the side. And so that's not going to work anymore because you're not going to be amplifying the low pressure through the divergence here. So in order to keep everything vertically aligned, to keep your divergence sitting directly above your low center, you're going to need an environment that has relatively weak wind shear, not much of a change in winds with height. Going back a little bit here. Okay, so we need weak wind shear so as to keep everything vertically aligned. We also need some sort of pre-existing disturbance to kick the whole thing off. We need some sort of pre-existing disturbance to get the thunderstorms going. This is just like when we talked about thunderstorms. Thunderstorms need a trigger in order to get them going because in a conditionally unstable environment, it's only unstable when it's cloudy. And so you need something to lift the air up till it's cloudy. So you need some trigger to get the system going. It's basically the same idea here. We need some pre-existing disturbance to come through to produce a little bit of lifting to get these thunderstorms going so that the whole thing can start to get organized. And as we mentioned, in many cases, especially in the Atlantic, that pre-existing disturbance is one of these things called an easterly wave that propagates across the Atlantic from Africa. Generally, they're actually produced by convection, by thunderstorms over the highlands of Africa. They produce these waves that propagate across the Atlantic. And then when they propagate over the warm ocean water, they can get the whole thing started and start to form hurricanes. Okay, and then the final ingredient that we need is at least some Coriolis force to get the system rotating. It turns out that if you don't get the system rotating, typically it won't organize. And so in order to get the system to organize into these rain bands and so forth and so on, you're going to need a little bit of rotation, and it's the Coriolis force that's going to supply that. So we need some Coriolis force. Now, by extension, what that implies is that we're probably not going to get a whole lot of hurricanes right at the equator, because remember, right at the equator, the Coriolis force is pretty small. So you're not going to have a lot of hurricanes that form right at the equator. You also don't get many storms that are going to cross the equator for the same reason, because if they start to approach the equator, the Coriolis force gets pretty small, and the system kind of falls apart. Stops rotating and kind of falls apart. Okay, so these are the conditions we need to get a hurricane going. We need warm ocean water to produce lots of evaporation. We need a conditionally unstable environment, which is almost always true in the tropics. We need weak wind shear so that the whole thing stays aligned vertically and keeps the divergence over the low center at the ground. We need a pre-existing disturbance to get the whole thing going. And then we need some Coriolis force to keep the thing rotating and keep it organized. So we need all of these things, but if on any given day, if you're looking to see where a hurricane might form, probably the starting point is to look at this warm ocean water, because, again, you're going to need a lot of evaporation to feed these clouds. And if the ocean water falls below a certain temperature, you're probably not going to produce enough evaporation. And it turns out there's actually kind of a magic cutoff, a magic sea surface temperature, where if the temperatures are above that, you'll get enough evaporation to potentially support a system. But if the temperatures fall below that, then it's going to be too cold and you can't really form a hurricane. And that magic number turns out to be about 80 degrees Fahrenheit or 27 degrees Celsius. When the temperatures are above that, if all the other conditions are satisfied, then you might be able to produce a hurricane. But in places where temperatures are below that, you're just not going to get enough evaporation. In fact, even if you have a hurricane that's already formed and then it propagates into a region where temperatures are below this magic number, then it's likely that system's going to weaken and eventually die off. So, for instance, this figure down here is showing the temperature of the ocean water. It's referred to as the sea surface temperatures, which is the temperature of the ocean water at the surface of the ocean. And sort of the orangish colors here, if you look at the color bar at the bottom, are where you hit this 27 degrees Celsius or 80 degrees Fahrenheit region. So on this particular day, it's really this zone right in here, fairly close to the equator in this case, where you're likely to have enough evaporation to potentially support the formation of a hurricane. Now, of course, you still need the other ingredients also. You're going to need to have an environment with relatively weak shear, and you're going to need some pre-existing disturbance to kick it off. And you can't be too near the equator because you won't have enough Coriolis. So, for instance, in this particular case, this band of warm ocean water spanning the Atlantic here is pretty close to the equator, so you might not form any systems there. But up over here, once you start to get into the Caribbean, into the Gulf of Mexico, then you're starting to get some places where you're a little bit off the equator but still have warm ocean temperatures, so you might be able to form a system there. If we look climatologically, that is on average, where hurricanes are going to form. Well, again, they're going to form where all the ingredients are satisfied. And so the first thing is you need relatively warm ocean waters, and they can't be too near the equator. And so, for instance, over here near Asia, on either side of the equator, we still have relatively warm ocean water, and so we can produce typhoons and cyclones in this case. Right near the equator, it's not very likely that we'll produce much. Same thing over here in the Indian Ocean. And then off of the equator a little bit here in the Atlantic and in the Eastern Pacific as well. Now you'll note that there's not a whole lot going down here off the coast of South America. There's not a whole lot of hurricanes that form down here off of Brazil or off of, Ecuador and Peru, I guess. Regardless, you don't get a lot of hurricanes in this region. And the reason is that in most cases, the ocean temperatures in these areas are just a little too cold. And so even though it's in a favorable spot in terms of the Coriolis force, you're not likely to produce hurricanes just because you've got the water being a little bit too cold there. And I guess the last thing I'll point out about this is that we also have this requirement about having weak wind shear. And in some ways, that explains the variations that you see, or at least it has a big impact on the variations that you see from year to year in hurricanes, because there are some conditions that set up that tend to produce more wind shear in these areas, say in the Western Pacific or Western Atlantic here, or the Caribbean and Gulf of Mexico, where some years you'll just have a bit more wind shear there than other years. And so the years where you have that wind shear, you're not as likely to have hurricanes form than in the other years. Okay, and then finally, when do hurricanes form? Well, this one's pretty easy to understand because it's basically dependent on the sea surface temperatures. And remember, there's a lag between when you get your most direct insolation and when you have your highest temperatures. So our most direct insolation is way back here on June 20th, but it's really not until August here that we start to hit our highest temperatures in the ocean surfaces. And so that's when you start to get your peak of your hurricane season here into August, late August, and early September is really when you have your peak of the hurricane season here. So this figure is showing number of hurricanes as a function of time here, as you can probably read. And the yellow are hurricanes and the red are hurricanes and tropical storms, but they follow the same basic pattern. This is a little bit later than the peak temperatures at the ground, keeping in mind that water has a higher specific heat, and so its temperature is going to vary a little bit more slowly. Any of you guys who grew up near the coast, I'm not quite sure how it works in the Gulf. I'd have to think about it, but it's probably still true in the Gulf. Will recognize this because in the early summer, even when it's fairly warm outside in June, say, the ocean water is still going to be cold. So when you go swimming, I grew up on the East Coast, and so when we go swimming in June, ocean water was still pretty frigid. Whereas it was later in the summer, as it's been warming up all summer, and you start to hit your peak ocean water temperatures, the ocean gets to be pretty warm, and it can stay pretty warm through September and into early October, even when it's fairly cold outside. So we've got this lag between our peak insolation and when we hit our peak ocean temperatures. And that's when we're going to hit our hurricane season at peak ocean temperatures. Okay, I think we'll stop it there then. So signing off.